Hello, welcome to EMCH 578 and 744 Introduction to Aerodynamics and Flight Mechanics. Today we are going to finish chapter 4 but by talking about different types of stall conditions. In general, we have three different types of stall. One is the leading edge or LES stall. The second one is trailing edge or the TS stall, and then we have the thin airfoil stall. Okay. Let's start by leading edge stall. Leading edge stall is a scenario where the stall starts from the leading edge. As you can see in these pictures, we are increasing the angle of attack a little by little, and at some point there is flow separation happening. As you can see, at angle of attack of 15 degrees plus, this is where the stall condition happen, and this is where we're gonna see the decrease in maximum, the lift coefficient. This is essentially this at 15 degrees specifically is where you see the maximum lift coefficient. So leading edge stall is where the flow suddenly, this suddenly is the key term here, separates from the leading edge. When the flow separates from the leading edge, you're going to see the separated flow R over the airfoil. So separation doesn't start from the trailing edge and move towards the leading edge. It starts from the leading edge, and there will be a sudden, expansion of the separated flow to the whole airfoil. So sudden separation of flow from the leading edge. This is usually seen in relatively thinner airfoil. We are not talking about theoretically thin airfoils. You are just talking about airfoils that are thinner, on the thinner side. In general, their thickness ratio is usually between 10 to 16% of the chord length. And you can see in their CL versus alpha curve that there is a sharp peak in the vicinity of CL max. So there is no gradual arrival at the stall condition, a gradual decrease in the CL. You can see that the CL is increasing linearly until it reaches the stall point, which is not the case for the other types of stall. So trailing edge stall, on the other hand, so this is the peak, as you can see. Trailing edge stall, on the other hand, is a bit different. As you increase, let's look at this thicker airfoil. As you get this is visibly thicker. At 5 degrees, we don't really have a separate flow. At 10 degrees, we don't have a separated flow. At 15 degrees, there is a little bit of separation around the trailing edge, and there is a gradual movement of the separated flow from the trailing edge to the leading edge. And at angle of attack of 22.5 degrees, you can see the all of the upper surface of the airfoil is separated. The flow over all of the upper surface of this airfoil is separated. This is where you see the lowest lift coefficient. So the maximum lift coefficient is essentially reached just before this point. At this point, you are going to see a gradual decrease. So this is the word of the day for trailing edge stall, is a gradual, progressive movement of separation from the trailing edge towards the leading edge. This type of flow separation usually happens in the thicker airfoils. Now you are not going to see that sharp increase. We are going to take a look at scale versus alpha curve, so all of them side by side on top of each other, and you're going to see that the peak here for the trailing edge stall is much damper than the peak for the leading edge stall. And then the last one we want to talk about is called the thin airfoil stall. The thin airfoil stall is very similar to the leading edge stall in that the stall happens suddenly at the leading edge, but the difference is first of all, it results from this extreme thinness of the airfoil, which essentially means that we are dealing with flat plates Thin airfoils are defined airfoil which thickness is 2% of the chord length, and these sharp corners usually are responsible for triggering the saw, the sharp corners of the thin airfoil. But what the difference between a thin airfoil saw and the leading edge saw is the fact that thin airfoil saw happens at a much faster rate, and because they usually have a lower camber, their maximum lift coefficient actually is not going to be as high as the regular non-thin airfoil. If you put all of the lift coefficient versus angle of attack for airfoils that are very similar to each other, right? Exactly, not exactly the same airfoil, but very similar to each other. We can see a trailing edge saw at knockoff 44 to 21, a leading edge saw for knockoff 4412, and a thin airfoil which is done for a flat plate. As you can see, these two are not symmetrical, which essentially means that their zero lift angle of attack is going to be at the exact same point and a negative value. And then there is a linear increase, which is exactly the same for both of them. The only difference is the saw characteristics. You can see the CL is linearly increasing for the leading edge saw until it reaches a very sharp corner, and there is a sudden drop in the lift coefficient. CL max for the trailing edge saw is a bit lower, but the saw happens gradually, doesn't happen suddenly. Because there are benefits to both of these. You can get a higher lift coefficient using the LES saw, but you can have more control over your aircraft because of the gradual nature of the increase. Thin airfoil, on the other hand, does not even compare. The maximum lift coefficient is much lower than both of them, and the saw happen at a lower angle of attack compared to trailing edge saw and leading edge saw, compared to the NACA 4412 and 4421. Okay, so one of the parameters of interest for the stall calculations is the stall velocity. We usually calculate this velocity for a cruise flight. Okay. And lift coefficient has to be the maximum value it can be because of the nature of the stall. So lift coefficient at the stall point is always the maximum it can be for that specific airfoil. And what the cruise flight means is that our force, our lift force, has to be equal to the weight or the payload of the aircraft. So this is essentially a rearrangement of the definition of lift coefficient. We say lift coefficient is equals to lift divided by 1/2 rho v squared multiplied by the planform area, the wing area. This is the definition of lift coefficient. If you rearrange this and then replace lift with weight and CL with maximum CL, you will be able to calculate the stall velocity. The stall velocity is essentially the velocity at which you're going to get the maximum lift coefficient. And since after the stall, if you increase the velocity, if you try to increase the velocity further, there will be a sharp decrease in the lift coefficient, which will cause a sharp decrease in the lift itself, and this balance between weight and lift is not going to exist anymore, which essentially means that you're going to lose altitude. Okay. But how can we prevent that? How can we prevent or delay the stall condition essentially, or maximize the lift coefficient even further than the theoretical limit? We have to use high lift devices, flaps or slats. There are different scenarios, different cases, but they're essentially just extensions added to your airfoil that can be deployed at any time that is necessary. And these flaps and slabs and ailerons, as you can see, that are very important, a very important part of aircraft control. Okay, let's look at an example of the trailing edge flap. Trailing edge flap is installed at the back of the airfoil, and essentially it means that you can move the trailing edge. You can rotate the trailing edge. If you rotate the trailing edge in the positive direction, which is defined as this direction, then you are effectively increasing the camber of the airfoil. Increasing the camber of the airfoil means higher lift coefficient. So positive delta, positive angle is going to cause a higher lift, and negative delta is going to cause a negative camber, which is going to result in lower lift, which is all can be observed in this graph as well. We have a CL versus alpha for the vanilla airfoil, let's call it, and then when you add a positive angle to the system, your lift coefficient is going to increase. If you add a negative angle to your system, like this, because of the negative camber, your lift coefficient, maximum lift coefficient you're going to see is going to decrease. This will also change the zero lift angle of attack. Move it from, I guess, close to zero to negative for positive values of angle, and from close to zero to positive for the positive camber or negative camber that you have created in your system. Okay. There's also another small change that is happening, that is the location, the angle of attack at which the stall happens, that also moves with zero lift angle of attack. Essentially means that although with a trailing edge flap you will be able to get a CL max, higher CL max, but you will be also hit by a lower stall angle, because everything has moved into the left. Essentially everything has moved in this direction, to up and left. So if the angle of attack, if the maximum angle at which a stall happens is important to you, you have to actually deploy a negative delta, a negative angle, to create a negative camber for your aircraft to increase the maximum operational angle of attack. Okay. If maximum lift coefficient is what you desire, you have to create a positive angle to create a positive camber and then create a higher lift coefficient. Okay. As you can see, like increasing the angle, the flap angle even further to 50 degrees has increased the maximum lift coefficient significantly. You can see the lift coefficient has increased significantly. So this is a very effective, very good method to increase the maximum lift coefficient. There are other mechanisms in place that we can install at the leading edge instead of the trailing edge. We have the leading edge slats that look like this, leading edge droops that can actually move, and Kruger flaps that look like this. So essentially what happens with these type of mechanisms is that they are either going to increase the camber, as you can see, or they are going to control the flow. So two different mechanisms. Let's look at this example of a leading edge flap that is separates from your body and can move. As you can see, there is a streamline passing through that gap between the airfoil and the flap, and then reintroduced to the top of the airfoil. This is going to augment the flow attachment to the system. This is going to increase the flow attachment to the system, which means that it will definitely delay the stall. The stall happens because of flow separation. If you create a mechanism that attaches the flow and forces more attachment, you are going to see a later stall. And this is also obvious in the graph. So with leading edge flap activated, you can see the stall condition is delayed, which effectively means your maximum CL coefficient is also going to increase. And this is the only effect that the leading edge flaps have on your airfoil. It's a very, very, very useful effect that they have, because they increase the maximum lift coefficient at the same time as increasing the stall angle of attack. Okay. So you can see a comparison of all of the different mechanisms with each other in this graph. For example, for the plain and slotted flaps, which are case A and E, you can see with the plain flap, we already know that the CL is going to increase, but the location of the maximum angle of attack, you can have stall angle of attack, is going to decrease. So the value of it is going to decrease. If you make it a slotted flap, this is going to encourage the flow reattachment, because there's some streamlines from the lower surface pushed to the upper surface and cause reattachment or reduce the adverse pressure gradient. So we can have different examples of slotted flaps, triple slotted flaps, double slotted flaps, and so on and so forth. If you use an extended flap or a Fowler flap like this, not only you are going to increase the maximum lift coefficient, but you are also going to increase the slope, the lift slope. So you are going to reach a higher lift coefficient, but you are going to reach that higher lift coefficient sooner as the increase the slope without changing the zero lift angle of attack location. So your stall angle is going to reduce significantly, but the maximum lift coefficient is going to increase significantly on the other hand. So there's a compromise. You just have to choose here. And leading edge flap and slats, their effects are given to you in the third graph here. Depending on the type of mechanisms, you can increase the stall condition, you can increase the lift coefficient, you can increase the angle of attack, a stall angle of attack, or you can change the zero lift angle of attack and the slope. So the point is to delay the stall, or to have more control over the stall. It's a better word to use. To have more control over the stall condition, we can introduce high lift devices, leading edge snaps, trailing edge snaps and flaps, different mechanisms, different things that they can have different effects, increasing CL, decreasing CL, changing the slope, changing the stall angle, attack, all of those things. So to exert more control over a stall, you have to change the geometry of the airfoil. Okay. But let's see how these high lift devices actually work. Let's look at the basic airfoil. We have actually, I did mention this, but we're just going to go over it again. Basic airfoil has an angle of attack and a free stream velocity. For a plain flap that is deflected with positive angle delta, what's going to happen is your angle of attack is going to change, meaning that there will be an effective angle of attack, or a virtual angle of attack, if you will, that is different from the angle of attack for the basic airfoil. Why is this the case? It's because by deploying the plain flap, you are essentially effectively changing the chord of the airfoil. The chord of the new chord of the airfoil is this dashed line, versus the regular chord of the airfoil was this regular black line. So you have effectively changed the angle of attack. You have created a virtual angle of attack that your flow sees. And this is going to be the main driving factor behind the changing of the characteristics of the flight. The same mechanism applies with a deflected leading edge flap. exactly the same mechanism. There's an angle. By deploying this, you're changing the location of the leading edge, which effectively means that you're changing the location of the or the angle of the chord length, which means that you will be dealing with a virtual angle attack that is going to create a lot of change in your CL versus angle attack characteristics. For the extended trailing edge, you are effectively increasing the chord as well as inducing flow reattachment mechanisms. So on a regular aircraft, we have different mechanisms at play. This is a regular airfoil on a regular aircraft, on a common commercial airliner. The cruise configuration looks like a regular airfoil. During takeoff, when we need a lot of camber and a lot of lift at the same time, this is the configuration. During the landing, where you need a lot of control, when you have to be able to control your flow, this is the configuration. So combining, the point is that combining all of these together is going to help us control the stall conditions, control the movement of the aircraft. It's not just about increasing the lift and delaying a stall, it's more about control. As you can see, this is the semi-foil fully deployed at angle of attack of 25 degrees. You can see that there's a huge vortex shading here, but we have also, through these mechanisms, we have created an attached layer to the airfoil, which is going to minimize the effect of the separated region. So these high lift devices are going to have different effects on your aircraft, on your airfoil, and you have to choose wisely how much of an increase you want to see in your lift coefficient, how much complexity do you want to add to your system, because this system is a very complex system. Manufacturing this, maintaining this is much more complicated than the regular airfoil. So just have to make sure that you need the airfoil number 8 that has all of the bells and whistles. Sometimes you don't really need anything, you just can fly with a regular airfoil. Just have to make the calculations and do the correct design. Let's see a video, watch a video of an airfoil slabs deployed, and see the effect of that on the movement of air. The regular airfoil. This is a very long video. I'm going to make sure to upload this PowerPoint file if I haven't uploaded it previously, so you can go ahead and watch the video yourself, but please make sure to do so. And that is it for today's lecture. Thank you for joining me. Enjoy the rest of your day. Hopefully see you next lecture.